Welcome to this video. Today we're talking about the Platonic representation hypothesis. This paper was published in July 2024 and the overall idea of this paper is that different models from different domains trained on different data and with different model architectures are all converging to the same representation, and that's so-called the Platonic representation hypothesis. Let us just jump into the figure number 1, and then I think we can just skip the abstract here. So the most important part we can get out of this figure number 1. And here the Platonic representation hypothesis is actually visualized. Okay, we have like a real world called Z. Okay, and from that set we are making a projection in two domains. One is an image and one is text. And now the overall idea is that our learned embedding have the same abstract representations. This does not mean that if we are doing like the cosine similarity between both, and they come from different models, that the cosine similarity is the same. They measure the distance differently, and we will see this later. But the overall idea is, okay, we have a real world and we have projections like an image and text, and the abstract representation is identical if we scale our model up. So if our model gets more parameter, this even gets larger, this representation convergence. The authors trying to give us a small reason why both of those vectors or the representation from different domains are converging to one representation. And it's claimed here or written here: the resulting vector embeddings are all derived from the underlying reality in Z and thereby becoming aligned. So maybe we have different projection with images, video, text, but the reality keeps the same. So we are not changing the reality. And if we train now models with more and more data from Z, they are more aligned to understand Z and then getting the same representation, okay? And they named their paper after Plato, and Plato is like a Greek philosopher, and he developed the very famous allegory of the cave. We can see that in this picture, his idea, and the overall idea is that we have also here reality Z, and we are doing a projection onto the wall, and the people here can just see the shadows, so just can see the projection of the real world, and that's also the same as our neural network. We have a projection into like image from the real world, and our neural network can just see the image, and they're trying to understand the real world. And because we are getting it from the same distribution Z, the representations are converging. Okay, I think we read the most important part of the introduction. Maybe just let's talk about this one. We just have a representation. What is it? It's just that we have like a data, we fed it into our neural networks and get out a feature vector. And then one important part is that we have a kernel. And a kernel measures a distance between two data points. And we could just calculate, for example, or use the dot product, but there's a reason we can't do this for this task here. And let's find out together why we can't just use the dot product. And the reason is very easy actually. If let's say we have two models, one is called ResNet, the other one is the vision transformer. Both are trained on image data, and now we are putting the same image into the ResNet and the vision transformer, and we are getting out a vector. And now the idea of the authors is that if this is the same image, so I don't know, we have just a dog or something, and here the same, and then those vectors should be in the same space, but or have the same abstract representation. That is what the authors are saying, and they're not in the same space because obviously this model can just learn that the first dimension is has a different meaning than the first dimension here. And And this is why we measure the distance with the so-called mutual nearest neighbor metric. And let's try to understand this. How does a mutual nearest neighbor metric work? Okay, let's say we have a high dimensional space from two models, and we have the same as before. We have a picture of our dog, and in the first model, so this is our ResNet, and this is the vision transformer, and this one here and this one here is our high dimensional space. Okay, and in the ResNet, the dog is visualized or is in the left corner of our high dimensional space, and in the vision transformer it's in a different space. And now, okay, now we are measuring not we are measuring the distance between dog and the nearest neighbors of dogs. And maybe here the nearest neighbor of dog is cat, and here it's also cat. And then we say, okay, both networks learned the same or a similar representation. But if instead of cat the nearest neighbor is car, for example, then we could argue, okay, the ResNet and the vision transformer are not learning the same representation. Mathematically, they are giving us a formula in the appendix. And yeah, we not just choose k to 1, but we choose like k, I don't know, 10. They chose 10 in this paper. And so they're looking at the 10 nearest neighbor. And if the average intersection between the one model and the other model is high, then we argue that they both learn the same abstract representation. Okay, we can see the formula here. We have one set from our k nearest neighbor from one model and the other one from the other model. Then we do the intersection, and we normalizing it by k, because k is our counts how many neighbors we have, and we want to make it independently from k. Okay, now it's important that we understood how the mutual nearest neighbor distance work, because they're using it for this experiment or for all their experiments, and they are using in this experiment 78 models, all from the same domain. So we are in the vision domain, so this can be a ResNet, a vision transformer, all kind of different models. So we actually see the models here. So we have models that are random initialized, we have models that are trained on classification, we have a mask autoencoder, we have models that trained with contrastive or with the clip. Okay, so a lot of different models. And now the question is, how is the performance on a downstream task called the Visual Task Adaptation Benchmark? So that's the name of the data sets. And can we see any patterns in the performance? And yes, we can see patterns if we look at this picture. Okay, we have a UMAT of model representation. A UMAP is just a projection from a very high dimensional space in 2D, so that we can as humans understand the distance in between different kind of models. And what we can now see is that we have two clusters. One is the blue and the other one is the red, and the red models are all getting less good results on the downstream task compared to the blue cluster. And the authors argue that this is one reason, or this support the theory of the Platonic representation hypothesis, because we see that all the models that are similar getting better results compared to those models that are maybe not trained on so much data, and therefore getting worse results on the benchmark. Okay, so we're seeing here that this model or all those models have maybe learned a same representation of the real world. Okay, so this experiment was for vision, but we also have some for language compared to vision models, and let's just understand this experiment. Okay, now we can see the comparison between different data domains. So we have vision and language combined, and therefore we use the Wikipedia caption data set, and we compare now different language model to the same vision models to the Dino V2. And it's also measured with the mutual nearest neighbor, but maybe let's try to understand how they did it this time. So we have again our high dimensional space, and we have our Dino V2 model, and we have one llama model, okay? And here we are putting into our Dino V2 model, we put the picture of the dog or the lion, or just a picture. And here we are using not the picture but the text. Okay, we are putting here the lion into the llama model, and in Dino V2 we are putting a picture of lion into the model, and then we have in our high dimensional space the lion is here, and again the lion in text is here. And now we take a second image, or now we are doing the same and calculating the nearest neighbor from this data point to all the other data points, and maybe we find out, okay, again here's cat the nearest neighbor, and also in Dino V2 cat is the nearest neighbor, and then we have a higher mutual nearest neighbor compared if they are not if lion is not in the same or cat is not in the same region, okay? And so this is how they calculated for the domain, language, and vision. And what we can see here now is on the x-axis the language performance. So as we go more to the right, the performance of language model gets better. And what we are seeing is that also the alignment gets higher. Okay, so if you have a higher language model which saw more data and was trained longer with more parameters, the alignment to Dino V2 gets stronger, and this is also one more point which support the overall idea that the models are combining, or if the models get larger and seeing more data, that they are coming to one learned abstract representation. And they're also showing it for CLIP, for MIE, and different vision models. And overall experiments are now clear, and let's try to understand why does this happen, what can the reason for it be, and therefore we jump into part 3 of this paper, why are representations converging. The authors are breaking up the reasoning into 3 parts, and all the 3 parts are derived from the equation how we are training models. And how we are training models, actually, we want to find the model that minimize our expected loss. So we have a lot of different models, and for those models we want to find the model that has a lowest expected loss. And then we have one more constraint, or sometimes even more constraint, but we always have or sometimes we have a regularization constraint. This can be the L2 norm of the weights, or L1 norm of the weights, or stuff like that, to regularize the network. And from this equation they derive 3 parts why representations can converge. And the first depends on the dataset and the loss function we are using. And they say if we have more different loss function we have to train on, so our task gets more and more harder, the possibility of our space that fits the task is getting smaller. Okay, let's maybe have a look at this figure. It's visualized it very good. So we have, for example, the first task, the space of our model is this, and if we're now adding more and more tasks, the possibility of our our models that can get good performance on all those tasks together is getting smaller and smaller and smaller. And because we are training large language models on a lot of different tasks, on the different domains, on a huge data set, the possibility space is maybe not so large, because all different models have to get to the same space, because there are not so many ways how you could fit all the tasks into one model. Okay, so this one is the first argument they are deriving from the equation, and let's now have a look at the second um, argument. And the second one is that we have a regularization, and they say that, okay, because of regularization our models tend to find simple functions. Okay, so that's, they also referred here anyway. Okay, so we can read it together. Such simplicity bias could be coming from explicit regularization commonly used in deep learning. However, even in the absence of external influences, deep networks naturally adhere to Occam's razor implicitly favoring simple solutions. Okay, so what are they saying? Even if we are not using regularization, all the models tend to find a very basic or very easy solution for a hard task, and not trying to think about the corner to finding a very special solution. They tend to find a simple solution. Okay, so this also makes our space smaller, so we have simple functions and we have functions that solve our task. And we see we have a lot of functions that could solve our task, so this is all this region here. But the only function that maybe our neural network will find is a simple function, because we have the simplicity bias. And the simplicity bias we can add to our neural network if we are using regularization, but the authors are also referring to a paper that's saying, okay, even if we don't use a regularization, we have the simplicity bias too. Okay, so now we can already get to the third point, and the third point is the function itself. And here we have to look at this figure, and the overall idea here is, okay, if we have more and more increasing our parameter size, so our models are getting larger, the intersection between those models on trying to find the minimum is getting higher. So on the left picture we see, okay, we have two small models both finding a local minimum, and if we are now scaling both of the models up, they are in a different region, but they can find the same minimum, because the minimum lies in both models. Okay, so this is the third argument. They are trying to make out of this equation. Maybe to sum it up, we can just read those boxes here, because they sum the three arguments up very cool. So the multitask scaling hypothesis, this one was the one about our loss, that if we have more tasks, the space is getting smaller. Okay, so as we train a more general model that solve more tasks at once, we should expect fewer possible solutions. And then we have a third box, capacity hypothesis. Bigger models are more likely to converge to a shared representation than smaller models. Okay, we saw this on this figure here, and it refers to our function f in our training equation. And then the last one, the regularization, we also should have a box anywhere, I would say. Yeah, the simplicity bias, Deep networks are biased toward finding simple fits to the data, and the bigger the model, the stronger the bias. Therefore, as model gets bigger, we should expect convergence to a smaller solution space. Okay, so I would say now we understand how they argue why the representations can converge or are converging. As we now understand what reasons there are for the converging of the abstract representation, let's find out what representations we are converging to. And we already talked about this at the beginning of the video, and the idea was that we have a reality set and we are doing a projection from the reality in our data domain, for example in text or in images or video or stuff like that. And then we try to understand the projection. And now the authors are saying if we understand the projection, the reality of the projection or the statistics that we learned about the projection is the same that as the reality. And it's just the same if we are doing a lot of constraints or a big constraint, but we can read it together in section 4.1, and here they are introducing a little bit more math. So we have given a probability distribution P of Z, and we can sample from P of Z T discrete events, and each event can be observed in various way. So we can observe it in or we map this into an arbitrary measurement space. So for example, we can map the real world into pixel, into words, into just any arbitrary number. So it doesn't really matter, but the important thing is the constraint here is that we have a bijective function, so that each observation we have exactly maps back to one exact event from our probability distribution. Okay, so this is the idealized world, and they say if we now understand the data, so our observations, then we also understand the underlying probability of a distribution of P of Z. And the next part, they are arguing that that contrastive learners converge to P of Z, so that if we train a contrastive model, so with a contrastive loss, that then the model is learning the real distribution P of Z. So a contrastive learner works very easy. So we have two data points, XA and XB, and if those data points can co-occur, for example, we have a data point with a dog and the other data point is also a dog, we want that the co-occurrence probability is high and therefore the dot product is high. Okay, and if we have one data point that's a dog and the other one is, I don't know, something complete different, then we have a negative pair, and the co-occurrence probability should be low. And they're defining the co-occurrence probability here, so they say, okay, we have a time window t, and how likely is that XA and XB are co-occur in this time window t together. Okay, and in the next step they are saying that the loss, so the dot product between the data points approximates the pointwise mutual information, and the pointwise mutual information gives us a probability how likely is it that the XA and XB co-occur dependent on their independence occurrence. Okay, so mathematically the PMI is defined like this. So we have the co-occurrence, and then we have the probability that X and Y happen observed independently from each other. And if we have high co-occurrence, and we have a high pointwise mutual information. Okay, so the dot product that is used to train the contrastive learner approximates our pointwise mutual information by some offset, and they're saying now, okay, if we have enough training data, and then our models is converging to the representation by the kernel PMI. Okay, so we can learn the pointwise mutual information of our data if we train our model with enough data, and so we are converging to the pointwise mutual information. And now the very last important step is we now have the probability of our data, but the data is not from our real data, so it's not from the real world, but from the projection. But because we said at the beginning that we have a bijective function, we can just rewrite it and say, okay, the co-occurrence is the same as in the real world, and therefore the pointwise mutual information between xa and xb is the same as set A and set B, and set A and set B is sampled by the same, or is a reality, and xa and xb is a projection of z. Okay, so if we learn with our data xa and xb, we can learn the real world and understand the statistics of it. And they're also saying this here, therefore for a modality in an idealized world, we observe representation converge to the same kernel, which represents certain pairwise statistics of P of Z. Okay, so here they are saying if we also have different projections, all those projections are learning the same statistics of P of Z. Okay, so that was, I think, a pretty interesting part with some math. And now we are actually at the end of the paper, and I just want to highlight one more part, and the last part is that the mutual nearest neighbor measurement we are using, they're saying it here, is 0.16. So let's read it together. We have shown results where different models arrive at similar but not the same representations. Figure 3, alignment clearly increases but only reach a score of 0.16 according to our mutual nearest neighbor metric. And the maximum for mutual nearest neighbor is 1, so 0.16 is not very high, and the overall question is, okay, so if we could we really say that they are converging, or are they still too different? But I think the very interesting part, or the thing that support the thesis, is that we have a positive trend in all those experiments here. So we see that the mutual nearest neighbor information increases if we scale our model and learn more data. So yeah, I would say they representations kind of converging. Okay, so I hope you enjoyed this video. I will put the link to the paper into the video description, and I hope we see us in the next video.